Alright fam, settle in, we're about to watch Legion Craft absolutely nail the art of building from scratch. First things first, before you can build anything, you need to know exactly where everything goes. We're talking precision land surveying here. The crew pound steel markers into the ground at specific coordinates. These aren't suggestions, they're gospel. Each marker indicates where a foundation pile belongs, and if you botch this step, you're basically asking for structural nightmares down the line. Once those markers are locked in, it's drilling time. The team bores vertical holes into the earth, sometimes manually, sometimes with machinery, right at each marker location. After the shafts reach proper depth, they fabricate reinforcement cages from steel rebar and lower them in. Next up is sand prep, which sounds boring, but stick with me. After spreading sand across the work area, massive compaction machines lumber through like mechanical elephants, crushing everything down. Workers follow up with handheld plate compactors, methodically pressing every square inch to eliminate voids and air pockets. The result, a rock-solid sand base. Immediately after compaction, they lay down polyethylene sheeting, basically a giant plastic blanket that tells groundwater to back off. Now we get to the underground utility party. High-density PVC pipes, bright orange, impossible to miss, snake across the compacted sand in carefully planned routes. These conduits will eventually handle drainage, sewage, and ventilation for the entire building. The crew secures everything with steel straps and heavy-duty clamps, because the last thing you want is pipes floating around when concrete flows in later. The foundation slab pour is happening now, and it's honestly mesmerizing to watch. The crew doesn't just dump and walk away. They're constantly monitoring, smoothing, and leveling as wet concrete spreads. After this beast fully cures and hits design strength, the real vertical construction begins. For the walls, they've gone with autoclaved aerated concrete blocks, AKC for short. These things have completely blown up in residential construction recently, and honestly, it's deserved. AKC blocks check basically every box: excellent thermal insulation, solid structural performance, relatively easy installation, lightweight enough that workers aren't destroying their backs, and fire resistance that'll make your insurance agent happy. Perfect for buildings where actual humans will be living. The installation process is meticulous, bordering on obsessive. Every single block gets checked with spirit levels and gently tapped into position with rubber mallets. Both horizontal and vertical alignment matter equally here. There's zero room for close enough. Here's the thing about masonry. Small errors compound exponentially as walls rise. A millimeter off at course 3 becomes a centimeter off at course 15. So the crew makes micro adjustments constantly. This specialized cement-based adhesive is legitimately impressive. It creates joints measuring just 1 to 3 millimeters thick. Compare that to conventional mortar joints that run 10 to 15 millimeters, and you start understanding why this matters. Those ultra-thin seams dramatically reduce thermal bridging. Fancy talk for places where heat sneaks through your walls. The application process uses notched trowels that create uniform ridges, ensuring consistent adhesive coverage and maximum bond strength between blocks. Strategic reinforcement comes next, installed wherever the structure needs additional backbone. The crew carves horizontal channels along the tops of specific block courses, then slides steel rebar into these grooves. These reinforced layers, engineers call them ring beams or bond beams, serve a critical purpose, distributing lateral forces and managing tensile stresses that would otherwise crack the masonry. This reinforcement strategy directly addresses AAC's inherent weakness. Under compression, AAC performs beautifully. Stack weight on top and it'll support loads all day. But subject it to pulling or twisting forces, that's where problems emerge. The solution involves cutting shallow horizontal grooves into block surfaces, creating channels where steel reinforcement can nestle securely. Why use heavyweight materials like solid concrete or reinforced brick throughout when you don't need to? This hybrid approach exploits AAC's advantages, low weight, superior insulation, while compensating for its limitations through strategic reinforcement. You'll also notice this system gave the construction team considerable flexibility in sizing and positioning window and door openings without compromising structural integrity. AAC excels at handling compressive loads, but here's the reality check. Tension and shear forces are its kryptonite, and every opening you introduce creates a vulnerable point. Windows and doors disrupt the continuous load path that channels weight from upper floors down to the foundation. The wall section spanning above these openings still needs to support everything overhead, while redirecting those forces around the gap. That's precisely why reinforcement gets systematically integrated into the block courses. It's not optional, it's structural necessity. The team now pivots to constructing auxiliary concrete sections that connect to the main structure. They excavate and level ground within designated perimeters, and where soil conditions demand it, they install compacted sand layers to create stable foundation bases. In certain locations, they roll out polyethylene membranes underneath to block subsurface moisture migration. After formwork is erected, fill material is placed and rebar is positioned. Fresh concrete gets pumped into the molds. Every cement-related operation receives careful supervision. You'll notice this attention to detail consistently throughout the project. Beyond the primary building, concrete also shapes various exterior features that integrate with the house. Now attention shifts toward preparing for roof installation. The crucial first step involves rolling waterproofing membrane across the newly poured concrete ring beam, crowning the walls. This bitumen or polymer layer establishes a horizontal moisture barrier that prevents capillary action from wicking water upward through the masonry, basically stopping your walls from becoming vertical sponges. The timber beams being positioned now are ceiling joists that will support both roof and interior ceiling systems, and they're designed to span the building's full width. They rest directly atop that ring beam, spaced according to engineering calculations that account for total roof assembly dead loads plus expected live loads. Workers rely on temporary scaffolding and elevated platforms for safe handling and positioning of these sizable beams. Heavy-duty metal hardware, joist hangers, anchor bolts, lag screws, steel brackets secures these timber members firmly to the concrete ring beam below. These connections prevent displacement when wind loads or seismic activity try pushing things around. Solid blocking or cross-bracing installed between joists add substantial rigidity to the entire framework. The team distributes concentrated load points across broader surface areas, significantly improving the structure's ability to resist bending and torsional stresses when roof loads bear down. Here's what makes this genuinely interesting. These wooden members aren't merely passive support elements. They create what amounts to a three-dimensional load-sharing network throughout the building. When properly connected, the masonry walls receive lateral bracing that prevents buckling or movement when external forces hit them. Next comes the genuinely exciting part, as the crew begins assembling the pitched roof system. This stage demands serious precision. Sure, it delivers aesthetic appeal, but the real advantage is performance in the local climate. Achieving exact timber cuts and proper alignment creates those triangular geometries that provide inherent stability. Configured this way, the entire roof functions as an integrated unit that directs vertical loads downward. Simultaneously, any lateral forces get transferred down into those reinforced masonry walls and ring beams constructed earlier. What makes the hip roof configuration particularly effective is wind resistance. The multi-slope design naturally deflects air currents that would otherwise generate uplift forces trying to peel the roof away. Additionally, having slopes on all four sides means precipitation doesn't accumulate. Rain and snow shed immediately. The precision of rafter connections at hip and ridge intersections matters enormously, and utilizing gusset plates, structural bolts, and heavy-duty metal connectors creates a framework that properly distributes loads. These junction points prevent lateral displacement and rotational movement, dissipating both shear and compression forces appropriately. Then there are those roof overhangs extending beyond the wall face. The rafters simply continue past the exterior wall line, and this serves multiple practical functions. Primarily, they project rainwater away from the building envelope, so moisture doesn't infiltrate walls and cause deterioration. Beyond that, these same overhangs block direct solar radiation from striking windows and exterior walls during hot weather. If you're questioning whether this matters, it absolutely does, because reducing solar heat gain can dramatically decrease interior temperature rise. It's actually an intelligent passive cooling strategy that stems from understanding regional climate patterns and building physics. Once underlayment goes down, they fasten horizontal strips called counterbattens directly over the rafters. Then comes OSB, those large engineered wood panels, which gets installed across certain sections to provide the roof diaphragm with necessary resistance against lateral forces. During OSB installation, they maintain small gaps between panels, allowing for thermal expansion and contraction as temperatures fluctuate. Following that phase, the crew lays down underlayment membranes and carefully positions waterproofing barrier sheets. The final layer consists of asphalt shingles, which have become the dominant choice because they offer flexibility, affordability, weather durability, and relatively straightforward installation. Workers position each shingle course with precision, fastening them using pneumatic nail guns. The overlapping pattern they create isn't merely decorative, it's engineered to channel water effectively away from the structure. Here's something fascinating. Thermal activation triggers adhesive strips on each shingle's underside, heat welding everything into a monolithic system. Meanwhile, critical detailing work occurs around two chimneys penetrating the roof plane. These aren't decorative elements, they're essential ventilation and exhaust pathways. Here's the challenge. Anywhere a chimney intersects a sloped rooftop, you've created a natural vulnerability where water infiltration loves to occur. That's why the crew installs elaborate weatherproofing using shaped metal flashings and specialized membrane systems. With the building envelope sealed tight, attention turns inward. After all, nobody wants a house that looks fantastic but feels uncomfortable. Before any finished flooring gets installed, the concrete substrate underneath requires serious preparation. The surface gets thoroughly cleaned and leveled until achieving absolute flatness. A penetrating sealer gets rolled on that soaks into the concrete's porous structure, binding loose particles and improving adhesion for subsequent layers. There's an additional benefit. This treatment functions as a moisture vapor barrier against water that might otherwise migrate upward through the concrete slab, a genuine problem for certain flooring materials that react poorly to dampness. After this coating fully cures, the team proceeds with installing the finished floor surface. Beneath each individual plank lies adhesive spread with a notched trowel that leaves controlled ridges. This technique ensures complete back surface contact and prevents hollow areas that might fracture when subjected to foot traffic or thermal cycling. Small plastic spacers get wedged between planks, maintaining uniform joint widths and preventing edge lippage where one plank sits higher than its neighbour. The installation follows a staggered pattern resembling traditional hardwood flooring. It's not purely aesthetic. This layout actually distributes weight more effectively and accommodates slight dimensional changes when temperatures and humidity levels shift. Now let's head outdoors, where the landscaping is genuinely going to transform this property. Preparing this much exterior space represents a massive undertaking. What happens here impacts more than visual appeal. It influences site drainage patterns and even creates microclimates around the building. Executed properly, this groundwork actually protects the foundation by managing stormwater and surface runoff correctly. Workers remove debris, broken concrete chunks, buried root masses, construction waste remnants. Simultaneously, they break up and cultivate existing soil, opening drainage pathways and giving future plant roots space to establish.